Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In 1964, two radio astronomers at Bell Telephone Laboratories in Holmdel, New Jersey, faced a maddening problem. Arno Penzias and Robert Wilson were attempting to calibrate a sensitive 20-foot horn antenna originally built for satellite communications, but everywhere they pointed their instrument across the sky, they detected the same persistent, low-level radio static. This wasn't the kind of interference they expected from earthbound sources. It was something far more mysterious and universal. The Holmdel horn antenna, as it became known, was a marvel of engineering precision. Built in 1959 for Project Echo, an early satellite communication experiment, the antenna was designed to detect the faintest radio signals bouncing off reflective satellites orbiting Earth. Its horn-shaped reflector, constructed with meticulous attention to minimizing unwanted noise, should have been capable of detecting signals with extraordinary sensitivity. However, when Penzias and Wilson began their systematic survey of radio sources in the Milky Way galaxy, they encountered an unexpected obstacle. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The mysterious signal appeared as a steady hiss equivalent to a temperature of approximately 3.5 degrees Kelvin above absolute zero. This might seem insignificant, but in the realm of radio astronomy, where scientists measure cosmic phenomena against the near absolute zero of empty space, even tiny temperature variations carry profound implications. The signal was isotropic, meaning it appeared identical regardless of which direction they pointed the antenna, toward the galactic center, toward empty space between stars, or even toward the horizon where Earth's atmosphere might contribute interference. Initially, Penzias and Wilson suspected terrestrial contamination. They methodically eliminated potential sources of the mysterious noise. Could it be interference from nearby New York City? They ruled out urban radio frequency pollution. Perhaps the signal originated from their electronic equipment. Extensive testing revealed no instrumental artifacts. They even discovered that pigeons had been nesting inside the antenna's throat, leaving what Wilson diplomatically termed white dielectric material coating the metal surfaces. The researchers carefully cleaned the antenna and relocated the birds, but the persistent 3.5-degree signal remained unchanged. The temperature measurement itself deserves explanation. In radio astronomy, scientists often express signal strength in terms of equivalent temperature. The temperature, a perfect blackbody radiator, would need to emit the same intensity of radio waves. This cosmic microwave background, as it would later be named, corresponded to the thermal radiation of an object cooled to just 2.7 degrees Kelvin, merely 2 7/10 degrees above the absolute zero temperature where all atomic motion ceases. Frustrated by months of unsuccessful troubleshooting, Penzias mentioned their predicament during a telephone conversation with Bernard Burke, a radio astronomer at the Massachusetts Institute of Technology. Burke immediately recognized the potential significance of their findings. He informed them that theoretical physicists at nearby Princeton University, led by Robert Dicke, had been predicting the existence of exactly such a signal, leftover radiation from the Big Bang itself. This moment represents one of science's most elegant examples of theoretical prediction meeting observational discovery. While Penzias and Wilson had been struggling with what they considered an annoying source of noise pollution, cosmologists had been calculating that the universe should be filled with the cooled remnants of its own creation. The stage was set for a revolutionary understanding of cosmic history, transforming an engineering problem into a window through which humanity could observe the universe's earliest moments. The theoretical foundation for cosmic microwave background radiation emerged from the brilliant minds of three physicists working in the aftermath of World War II. George Gamow, a Ukrainian-American cosmologist, along with his graduate student, Ralph Alpha, and colleague Robert Herman, developed calculations that would predict one of the universe's most fundamental signatures nearly 2 decades before its accidental discovery. In 1946, Gamow began investigating the implications of Georges Lemaitre's expanding universe model, which suggested that if the cosmos was currently expanding and cooling, it must have been much hotter and denser in the past. Gamow reasoned that during the universe's earliest epochs, temperatures would have been so extreme that atomic nuclei could not hold on to electrons, creating a plasma of free protons, neutrons, and electrons in thermal equilibrium with intense electromagnetic radiation. Alpha's 1948 doctoral dissertation, famously known as the Alpha-Beta-Gamma paper, due to Gamow's addition of physicist Hans Bether's name for the Greek letter sequence, provided detailed calculations of primordial nucleosynthesis. This work demonstrated how the lightest elements, hydrogen, helium, and traces of lithium, could have formed during the universe's first few minutes, when temperatures dropped sufficiently for nuclear fusion to occur without immediately being disrupted by energetic photons. The key insight came from understanding recombination, the epoch when the universe cooled enough for electrons to combine with atomic nuclei, forming neutral atoms for the first time. Before recombination, approximately 380,000 years after the Big Bang, the universe was opaque to light because free electrons scattered photons continuously. Hermann and Alpha calculated that when the temperature dropped to approximately 3,000 degrees Kelvin, electrons would finally bind to nuclei, making the universe transparent and allowing light to travel freely through space. This moment of cosmic transparency, termed the surface of last scattering, would have released a flood of thermal radiation corresponding to the universe's temperature at that epoch. However, the subsequent expansion of space would stretch these photons, redshifting them from visible and infrared wavelengths into the microwave portion of the electromagnetic spectrum. By 1948, Hermann and Alpha had calculated that this relic radiation should be observable in the present day as a nearly uniform background signal with a temperature of approximately 5 degrees Kelvin. Robert Dicke, working at Princeton University in the 1960s, independently arrived at similar conclusions while investigating alternative cosmological models. Dicke's team, including James Peebles, David Wilkinson, and Peter Roll, were actually constructing their own microwave antenna to search for this predicted background radiation when they learned of Penzias and Wilson's puzzling observations at Bell Labs. The theoretical prediction rested on several fundamental assumptions about the universe's structure and evolution. First, the cosmological principle suggested that the universe appears roughly uniform and isotropic when viewed on large scales, meaning the background radiation should appear nearly identical in all directions. Second, the assumption of thermal equilibrium in the early universe implied that the radiation would exhibit a nearly perfect blackbody spectrum with intensity distributed across frequencies according to Planck's law. These theoretical foundations also predicted specific relationships between the background radiation's temperature and other observable cosmic parameters. The theory suggested that regions of slightly higher or lower density in the early universe would leave corresponding temperature fluctuations in the background radiation. These minute variations, expected to be only microkelvin in amplitude, would represent the seeds from which galaxies and large-scale cosmic structures eventually grew under gravitational influence. The theoretical framework provided testable predictions that distinguished cosmic background radiation from other possible sources of microwave emission. Unlike radiation from stars, galaxies, or interstellar dust, the cosmic microwave background should exhibit no correlation with visible matter distributions, no seasonal variations, and no preferred directions in space. These characteristics would become crucial for confirming that Penzias and Wilson had indeed detected the universe's primordial afterglow, rather than some unknown astrophysical phenomenon. Robert Dicke sat in his Princeton University office in 1964, contemplating one of cosmology's most pressing questions. Could the universe's thermal history be directly observed? As a theoretical physicist with a keen understanding of both quantum mechanics and general relativity, Dicke had been developing his own version of Big Bang nucleosynthesis theory, independent of the earlier work by Gamow, Alpha, and Hermann. His calculations consistently pointed toward the same remarkable conclusion. The universe should be filled with detectable microwave radiation left over from its hot, dense beginnings. Dickey assembled a small but brilliant team to test this prediction experimentally. James Peebles, a young theoretical physicist, refined the calculations of primordial nucleosynthesis and cosmic background radiation temperature. Peter Roll and David Wilkinson, both skilled experimentalists, began designing and constructing a sensitive microwave receiver specifically optimized to detect the predicted cosmic signal. Their instrument, mounted on the roof of Princeton's Palmer Physical Laboratory, was nearly ready for operation when an unexpected telephone call changed everything. The call came from Bernard Burke at the Massachusetts Institute of Technology, who had just spoken with Arno Penzias about the mysterious noise plaguing the Bell Labs antenna. Burke immediately recognized the potential connection between Penzias and Wilson's observational puzzle and Dickey's theoretical predictions. When Burke relayed this information to Dickey, the Princeton physicist realized that the cosmic microwave background might already have been discovered just 30 miles away in Holmdel, New Jersey. Dick's reaction was famously understated. According to his colleagues, he simply hung up the telephone, turned to his research team and announced, "Well, boys, we've been scooped." This moment represents one of science's most elegant convergences, where theoretical prediction and accidental observation met through pure serendipity and scientific communication networks. The Princeton team immediately contacted Penzias and Wilson, leading to a series of collaborative meetings that would transform both groups' understanding of their work. Peebles's theoretical calculations had predicted a background radiation temperature of approximately 10 degrees Kelvin, which was remarkably close to the 3.5-degree signal detected by the Bell Labs antenna, especially considering uncertainties in cosmological parameters available at the time. Dickey's approach to the cosmic background radiation problem differed subtly but importantly from earlier theoretical work. While Gamo's team had focused primarily on element formation during Big Bang nucleosynthesis, Dickey emphasized the thermal equilibrium conditions that would have characterized the early universe. His calculations incorporated more sophisticated treatments of photon-matter interactions during recombination, leading to more precise predictions of the background radiation's observable characteristics. The Princeton connection proved crucial for understanding the cosmological significance of Penzias and Wilson's discovery. Without the theoretical framework provided by Dickey's team, the Bell Labs astronomers might have continued searching for instrumental or terrestrial explanations for their mysterious signal. Conversely, without the serendipitous discovery at Bell Labs, the Princeton team might have spent months or years developing their own detection apparatus. Peebles played a particularly important role in establishing the theoretical context for the discovery. His detailed calculations showed how the cosmic microwave background temperature related to other fundamental cosmological parameters, including the universe's current density, expansion rate, and age. These relationships would prove essential for using background radiation measurements to constrain cosmological models and test Big Bang theory against alternative hypotheses. The collaboration between Princeton theorists and Bell Labs observers established a new paradigm for cosmological research. Rather than working in isolation, theoretical and observational cosmologists began to recognize the immense value of close cooperation between prediction and measurement. This approach would become increasingly important as cosmic microwave background research evolved from initial detection toward detailed mapping of temperature fluctuations across the sky. The Princeton connection also highlighted the importance of scientific communication networks in facilitating discoveries. Burke's telephone call to Dickey exemplified how informal professional relationships can accelerate scientific progress by connecting researchers working on related problems. This human element of scientific discovery often receives less attention than technical achievements, but it plays an equally crucial role in advancing human understanding of the universe. The announcement of the cosmic microwave background discovery came through an unusual pair of scientific papers published simultaneously in the Astrophysical Journal in 1965. The first paper, authored by Penzias and Wilson, bore the modest title, a measurement of excess antenna temperature at 4080 MHz. The second, written by Dickey, Peebles, Roll, and Wilkinson, provided the cosmological interpretation under the title Cosmic Black Body Radiation. This dual publication strategy reflected both the observational rigor required for such an extraordinary claim and the theoretical framework necessary to understand its implications. Penzias and Wilson's paper maintained a deliberately conservative tone, carefully describing their technical procedures and systematic elimination of potential error sources. They reported detecting isotropic radiation equivalent to 3.5 degrees Kelvin at a frequency of 4.08 GHz, corresponding to a wavelength of 7 3/10 centimeters. The paper meticulously documented their efforts to account for atmospheric absorption, ground radiation, and instrumental artifacts, establishing the mysterious signal's cosmic origin through the process of elimination. The Princeton team's companion paper provided the cosmological context that transformed an engineering problem into a fundamental discovery about the universe's structure and history. They calculated that thermal radiation from a primordial fireball cooled by cosmic expansion over approximately 10 billion years should produce exactly the type of microwave background observed by Penzias and Wilson. Their theoretical framework connected the observed radiation to Big Bang nucleosynthesis, recombination epoch physics, and the large-scale structure of the observable universe. Initial reaction from the broader scientific community ranged from cautious interest to outright skepticism. Many astronomers questioned whether a single measurement at one frequency could definitively establish the cosmic origin of the detected radiation. Alternative explanations included previously unknown galactic radio sources, thermal emission from interstellar dust, or systematic instrumental effects that had somehow escaped detection during calibration procedures. The most significant challenge came from advocates of steady-state cosmology, particularly British astronomers Fred Hoyle, Thomas Gold, and Hermann Bondi. Their steady-state model proposed that the universe maintained constant average density despite expansion through continuous creation of new matter. This theory elegantly avoided the conceptual difficulties associated with a universe beginning from a singular, hot, dense state, but it provided no mechanism for producing the observed background radiation. Hoyle and his colleagues argued that the microwave background could originate from thermal emission by metallic dust grains distributed throughout intergalactic space. They calculated that iron or graphite particles heated by starlight and distributed at the appropriate density might produce radiation indistinguishable from primordial thermal emission. This alternative explanation gained temporary credibility because it could potentially account for the observed isotropy and temperature without requiring exotic early universe conditions. The controversy intensified debates about fundamental cosmological questions that had divided astronomers for decades. Big Bang models predicted a universe with finite age and evolving physical conditions, while steady-state theory described an eternal cosmos with unchanging properties. The cosmic microwave background represented the first observational evidence, capable of decisively testing these competing worldviews. Verification efforts began immediately following the initial announcement. Radio astronomers around the world attempted to confirm Penzias and Wilson's measurements using independent instruments and different observational techniques. The Soviet Union's radio astronomy facilities at Pulkovo Observatory detected similar signals, as did observers using the 300-foot telescope at Green Bank, West Virginia. Each successful detection strengthened confidence in the phenomenon's reality, while ruling out systematic errors specific to the Bell Labs antenna. However, definitive confirmation required measurements across multiple frequencies to test whether the radiation exhibited the characteristic blackbody spectrum predicted by Big Bang theory. A perfect blackbody radiator emits electromagnetic radiation with intensity distribution determined solely by temperature, according to Planck's law. Cosmic background radiation should follow this precise mathematical relationship with peak emission at millimeter wavelengths corresponding to its 2.7 degree Kelvin temperature. Early spectral measurements proved technically challenging because Earth's atmosphere absorbs many of the relevant frequencies, requiring balloon-borne or space-based instruments for accurate observations. Ground-based measurements at centimeter wavelengths provided limited spectral coverage, leaving room for alternative interpretations of the radiation's origin and nature. The need for comprehensive spectral confirmation would drive the next phase of cosmic microwave background research, ultimately leading to space-based missions designed specifically to map the universe's thermal afterglow with unprecedented precision and accuracy. The decade following Penzias and Wilson's discovery witnessed an explosion of technological innovation aimed at mapping the cosmic microwave background with ever-increasing precision. Ground-based observations, while foundational, faced fundamental limitations imposed by Earth's atmosphere, which absorbs and emits radiation at many of the frequencies crucial for understanding the background radiation's spectral characteristics. The solution required lifting sensitive detectors above the atmospheric interference, launching an era of space-based cosmology that would revolutionize our understanding of the universe's structure and evolution. The first major breakthrough came from balloon-borne experiments conducted throughout the 1970s and 80s. These high-altitude missions carried cryogenically cooled detectors to altitudes exceeding 100,000 feet, where the thin atmosphere posed minimal interference with cosmic microwave observations. Balloon experiments confirmed that the background radiation followed a nearly perfect black-body spectrum, with temperature precisely measured at 2.725 degrees Kelvin. This spectral confirmation eliminated alternative explanations involving interstellar dust emission, definitively establishing the radiation's primordial origin. However, the most revolutionary advance came with the Cosmic Background Explorer, or COBE, launched by NASA in 1989. This dedicated space mission carried 3 sophisticated instruments designed to measure different aspects of the cosmic microwave background with unprecedented accuracy. The Far-Infrared Absolute Spectrophotometer, known as FIRAS, measured the background spectrum across infrared and submillimeter wavelengths, while the Differential Microwave Radiometer, or DMR, searched for tiny temperature variations across the sky. OBE's spectral measurements revealed that the cosmic microwave background follows a black-body curve with extraordinary precision, the most perfect black-body spectrum ever observed in nature. The temperature variations detected by DMR were even more significant for cosmology. After subtracting the motion of our solar system through space, which creates a dipole temperature pattern due to Doppler effects, COBE revealed minute fluctuations at the level of mere tens of microkelvin across the cosmic background. These temperature fluctuations, announced in 1992, represented the first direct observation of primordial density variations that would eventually grow into galaxies, galaxy clusters, and the cosmic web of large-scale structure we observe today. John Mather, COBE's principal investigator, famously described the discovery as seeing the face of God, while team member George Smoot declared it the discovery of the century, if not of all time. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, provided dramatically improved angular resolution and sensitivity compared to COBE, positioned at the second Lagrange point, approximately 1.5 million kilometers from Earth. WMAP operated in a thermally stable environment, ideal for precision microwave observations. The mission's 9-year observation campaign produced detailed maps revealing the cosmic microwave background's temperature variations with unprecedented clarity and statistical significance. WMAP's results transformed cosmology from a data pour to a precision science. The mission's measurements of temperature fluctuation patterns across different angular scales provided direct tests of cosmological models, constraining fundamental parameters including the universe's age, composition, and geometry. The data revealed that ordinary matter comprises only 4.6% of the universe's total energy density, with dark matter accounting for 22.8% and dark energy representing the remaining 72.6%. The European Space Agency's Planck mission, operational from 2009 to 2013, represented the culmination of cosmic microwave background mapping technology. Planck's instruments achieved sensitivity and angular resolution sufficient to extract essentially all accessible cosmological information from temperature fluctuations, limited only by fundamental astrophysical foregrounds and cosmic variance, rather than instrumental capabilities. Planck's legacy extends beyond improved measurements to encompass new discoveries about the universe's fundamental properties. The mission detected evidence for cosmic inflation, the hypothetical period of exponential expansion during the universe's first fraction of a second. Planck's polarization measurements revealed information about primordial gravitational waves and provided independent confirmation of the standard cosmological model's predictions. Modern cosmic microwave background research continues pushing technological boundaries through ground-based experiments targeting polarization signals too, faint for space missions to detect economically. Projects like the Atacama Cosmology Telescope, South Pole Telescope, and proposed CMB Stage 4 initiative aim to detect primordial gravitational wave signatures in the background, radiation's polarization patterns, potentially providing direct evidence for cosmic inflation and quantum gravity effects during the universe's earliest moments. The cosmic microwave background represents humanity's most ancient photograph of the universe, capturing its appearance when it was merely 380,000 years old, less than 0.03% of its current age. This primordial snapshot, encoded in minute temperature variations across the sky, contains a wealth of information about fundamental cosmological parameters that govern the universe's structure, composition, and ultimate fate. When cosmologists analyze the cosmic microwave background's temperature fluctuations, they discover patterns that reveal the universe's acoustic oscillations during its earliest epochs. Before recombination, the cosmos was filled with a tightly coupled plasma of photons, electrons, and atomic nuclei. Sound waves propagated through this primordial fluid, creating regions of compression and rarefaction that would leave distinctive imprints on the background radiation's temperature distribution. These acoustic peaks, visible in the cosmic microwave background's power spectrum, function like cosmic DNA, encoding information about the universe's fundamental properties. The angular scale of the first acoustic peak directly measures the universe's spatial curvature, revealing that space is remarkably flat on large scales. The relative heights of subsequent peaks constrain the densities of ordinary matter, and dark energy with precision unmatched by any other cosmological probe. The temperature fluctuations themselves tell a compelling story about cosmic structure formation. Regions that were slightly denser than average during the recombination epoch appear as warm spots in the cosmic microwave background, while underdense regions create cold spots. These density variations, originally produced by quantum fluctuations during cosmic inflation, would grow under gravitational influence to form the cosmic web of filaments, galaxy clusters, and voids that characterize the modern universe's large-scale structure. Precise measurements reveal that the cosmic microwave background temperature varies by only about 100 microkelvin from its average value of 2.725 degrees Kelvin. This extraordinary uniformity reflects the universe's remarkable homogeneity on large scales, supporting the cosmological principle that underpins our understanding of cosmic evolution. However, the minute fluctuations that do exist were crucial for structure formation. Without these primordial seeds, the universe would have remained a smooth, featureless expanse devoid of stars, galaxies, and planets. The cosmic microwave background's polarization patterns provide additional insights into primordial physics. Polarization arises when photons scatter off free electrons, creating preferred orientations in the electromagnetic field oscillations. Two types of polarization patterns, designated E-mode and B-mode, carry different cosmological information. E-mode polarization correlates with temperature fluctuations and confirms our understanding of recombination physics, while B-mode polarization potentially carries signatures of primordial gravitational waves generated during cosmic inflation. Analysis of these patterns has enabled cosmologists to determine the universe's age with remarkable precision. 13.8 billion years, with an uncertainty of less than 1%. The measurements also reveal that the universe will expand forever, driven by dark energy's repulsive effects, rather than eventually collapsing under gravitational attraction. This conclusion follows from observations showing that dark energy comprises approximately 68% of the universe's total energy density. The cosmic microwave background data also provides crucial insights into the physics of Big Bang nucleosynthesis, the process that forged light elements during the universe's first few minutes. The measured abundance of ordinary matter, determined from acoustic peak analysis, precisely matches theoretical predictions for the production of hydrogen, helium, and lithium in a hot, dense early universe. This agreement represents one of Big Bang cosmology's most compelling confirmations. Perhaps most remarkably, the cosmic microwave background measurements constrain the number of neutrino species in the universe. These nearly massless particles, produced abundantly during Big Bang nucleosynthesis, subtly influence the radiation's temperature and polarization patterns. Current observations confirm the existence of exactly 3 types of light neutrinos, consistent with particle physics experiments, but derived from completely independent cosmological observations. The precision achieved in cosmic microwave background cosmology has transformed our understanding of dark matter's properties. While we cannot directly observe dark matter particles, their gravitational effects on primordial acoustic oscillations reveal that dark matter interacts very weakly with ordinary matter and radiation. This information guides experimental searches for dark matter particles in underground laboratories and particle accelerators worldwide. Modern cosmic microwave background research continues revealing new aspects of primordial physics through increasingly sophisticated analysis techniques. Scientists now use machine learning algorithms to extract subtle correlations in the data, search for non-Gaussian signatures that could reveal exotic physics during inflation, and combine multiple datasets to constrain extensions to the standard cosmological model. Each advance brings us closer to understanding the fundamental processes that shaped the universe during its first moments and continues to govern its evolution today. The accidental discovery of the cosmic microwave background fundamentally transformed humanity's understanding of the universe, establishing Big Bang cosmology as the standard model for cosmic evolution and opening new frontiers in theoretical and observational astronomy. What began as an engineering problem with a radio antenna evolved into one of the most profound scientific discoveries of the 20th century, earning recognition through Nobel Prizes and inspiring generations of cosmologists to probe ever deeper into the universe's mysteries. In 1978, Arno Penzias and Robert Wilson received the Nobel Prize in Physics for their discovery of cosmic microwave background radiation. The Nobel Committee specifically recognized their detection of the thermal radiation predicted by theorists studying the consequences of the Big Bang model of cosmology. This acknowledgement represented more than recognition of a single discovery. It marked the scientific establishment's acceptance of Big Bang theory as the most viable explanation for the universe's origin and evolution. The Nobel recognition extended beyond the original discoverers to encompass the broader theoretical and experimental framework surrounding cosmic microwave background research. In 2006, John Mather and George Smoot shared the Nobel Prize in Physics for their leadership of the COBE mission, which provided definitive measurements of the background radiation's blackbody spectrum and first detected the tiny temperature fluctuations that would become seeds of cosmic structure. The cosmic microwave background discovery catalyzed the development of precision cosmology, transforming the field from philosophical speculation to quantitative science. Before 1965, cosmologists worked with limited observational constraints, allowing multiple competing theories to coexist without definitive tests. The background radiation provided the first direct evidence for a hot, dense early universe, ruling out steady-state alternatives and establishing a framework for understanding cosmic evolution. This paradigm shift influenced every aspect of astronomical research, from studies of individual stars to investigations of large-scale structure. The cosmic microwave background measurements provided crucial boundary conditions for computer simulations of structure formation, enabling astronomers to model how primordial density fluctuations evolved into the cosmic web of galaxies and dark matter filaments observed today. These simulations, in turn, guided observational programs designed to test theoretical predictions about cosmic evolution. The discovery also spurred technological innovations that extended far beyond cosmology. Developing sensitive microwave detectors for space-based missions required advances in cryogenic engineering, superconducting electronics, and precision attitude control systems. Many of these technologies found applications in medical imaging, communications satellites, and materials science, demonstrating how fundamental research drives technological progress across multiple disciplines. Modern cosmic microwave background. Research continues pushing the boundaries of observational capability and theoretical understanding. Current ground-based experiments target B-mode polarization signatures that could provide direct evidence for cosmic inflation, the hypothetical period of exponential expansion during the universe's first fraction of a second. Detecting these primordial gravitational wave signatures would constitute another revolutionary discovery, comparable in significance to the original background radiation detection. The search for primordial B-modes represents one of cosmology's most technically challenging endeavors, requiring sensitivity improvements of several orders of magnitude beyond current capabilities. Projects like the proposed CMB Stage 4 initiative plan to deploy thousands of superconducting detectors at Antarctic and Chilean observatories, where dry atmospheric conditions minimize interference with faint polarization signals. Future space missions may probe even more exotic signatures in the cosmic microwave background, searching for evidence of cosmic strings, magnetic fields in the early universe, or departures from standard inflation models. These investigations could reveal connections between cosmology and fundamental physics, potentially providing insights into quantum gravity, extra dimensions, or the ultimate theory of everything that unifies all physical forces. The cosmic microwave background discovery exemplifies serendipity's role in scientific progress, demonstrating how unexpected observations can revolutionize human understanding when combined with theoretical insight and rigorous experimental verification. Penzias and Wilson's initial frustration with persistent antenna noise led to recognition that the universe itself was speaking to us through its thermal afterglow, carrying information about conditions during its earliest moments. This legacy continues inspiring new generations of scientists to pursue fundamental questions about cosmic origins, structure, and fate. The cosmic microwave background remains our most direct connection to the universe's birth, a fossil radiation that preserves information about physics under conditions impossible to recreate in terrestrial laboratories. As technology advances and theoretical understanding deepens, this primordial signal will continue revealing secrets about the cosmos, ensuring that an accidental discovery from 1964 remains at the forefront of 21st century science. The story of cosmic microwave background discovery reminds us that the universe's greatest secrets often reveal themselves through careful observation, theoretical insight, and the willingness to recognize profound truth hiding within mundane phenomena. From radiostatic to cosmic revelation, this journey embodies the essence of scientific discovery and humanity's eternal quest to understand our place in the vast cosmos.